Hi there everyone. In this video I'm going to talk about integration and areas. You've done some integration, we know how to do integrals of functions, so I want to get into the relationship now between the integral thing that we've been doing, that process of anti-differentiation, and what the actual applications of that is, and that is to area. So let me just give you a brief kind of rundown on this. It's pretty simple when you see me go through it. Imagine if you have a car traveling down a road and I was to do the velocity versus time graph. And this is going to be a pretty boring graph. This car is going 60 kilometers an hour. That's the speed, and there's 1 hour and there is 2 hours, okay? So I'll just look at it over this time period. Okay, so pretty boring graph. I think you could probably tell me there how far the car has travelled in those 2 hours. It's been going 60 kilometres an hour constantly for 2 hours. So you know that the car has travelled 120 kilometres. Now, it's also a fact that the area of this rectangle is 60 times 2, 120. Now there's a connection that people started seeing. It doesn't matter what kind of graph that you did. Let's say we've got a car doing this. So this is still the velocity. This is still time. Let's make this 1. Let's make this 2. Let's make that 60. Now this is a little bit harder question. How far has the car travelled now? So obviously this car is speeding up. It's starting from rest. It's got a constant acceleration, and after 2 hours it reaches 60 kilometers an hour. So this is very slow acceleration. So I could ask the question, well, how far has the car traveled in that time? And what we can work out is actually, like I showed you above, that the distance the car has traveled is the equivalent of the area under the graph. And you've probably seen that in physics before, right? So then this problem becomes really easy. If I can work out the area of this triangle, which is a half times the base times the height, we can also see that for this particular car, it's travelled 60 kilometres in those 2 hours. Making these connections is one of the great things that Newton did and Leibniz did when they came up with calculus. The connection between differential calculus and integral calculus we'll talk about later with the fundamental theorem, but just focusing on this, we know that the area under the graph here represents the distance travelled. So one of the things that we're looking at here is trying to work out the area underneath curved lines, not just straight lines are going across, but curved lines. So the way that this was approached is by working out the area of rectangles underneath the curve and adding up lots of them. So in calculus you get this idea of adding up lots and lots and lots and lots and lots. And coming up with a much simpler way of doing things. And this is what integration is all about. And you can see we've got 3 different ways of representing it here. If we wanted to work out the area under the curve, we could use the left-hand endpoints, we could use the right-hand endpoints, in which case we would overestimate the area under the curve, or we could use the centered rectangles, which is much better. Okay, so by the process of integration, we're working out the area underneath curves. You can see from this diagram here that we get a pretty good idea of what that area is just by adding up the area of all those rectangles. Okay, so what we normally do is the rectangles are normally the same width, so we call that width delta x, okay, a small change in x, and the rectangle here, the left-hand endpoint, let's say, is f of x at that particular x value. So we can work out the area of that rectangle is f of x times delta x. Okay, now the next rectangle is going to be f of x times delta x. Okay, so in this case we've moved a little bit further along, so there'll be a different value for f of x. So when we're working out the exact area, what we want to do is we want to add up lots of these. Okay, I'm going to say from I equals 1 to n. So let's say we had 20, 30, 40, 50 rectangles. In each case we take the value of f of x times it by delta x. That's the area of that rectangle. Then we add up the next one, we can add up the next one, we add up the next one. Okay, and you can see this is kind of going to lead to a formula here, like you did for differential calculus. This sum formula, using the word s, gradually became this thing here, which is an elongated s. That's the integral sign that we've been using. We normally say between which two values we're integrating or finding the area underneath of this curve f of x, and rather than writing delta x, we write dx. So that is the integral version of working out the area underneath the curve. If I just show you a little bit of a demo of that. Here we've got the curve x to the 4 minus 3x squared plus 1, and we're looking at the area under the curve, and you can see I've used 5 rectangles here going between 0 and 1. If I ramp that up and let's say make that 10 rectangles rather than 5, I'll just replot that. You can see now that you get an idea that the area that we're estimating is much closer to what the actual area underneath the curve is. Note also that the areas that are under the curve will count as negative for an integral. So all these areas up to about 0.6 here, just after 0.6, count as positive, but these areas down here will count as negative. So let's go for 100 rectangles and replot that. Now you can see that the area under the curve and the area of all those rectangles is almost identical. Okay, and you can see the estimated area and the actual area is almost the same. It's a pretty boring process to add up the areas of all those 100 rectangles, but again, we've got a way of doing this, a calculus way of doing this that makes life a lot easier. So going through this really quickly, what we could do is work out the area underneath y equals x squared from 0 to 4 using 8 rectangles. I reckon it'd be a pretty easy job for you to work out the area of those 8 rectangles. The gap each time, or the base, is always 0.5, and then the height, it depends on the x value. Okay, so let's take, and it looks like we're using the right endpoints in this question here, using right rectangles. Okay, so the first rectangle is at x equals 0.5, so the height of the rectangle, the y value is going to be 0.5 squared, so we've got 0.5, that's the base, times the height, 0.5 squared, plus base times height. Okay, the height of the next rectangle is going to be exactly 1, so that is the area of that rectangle. The next rectangle is base times height. You get my idea, don't you? Okay, so if we looked at that expression there, we could take out the 0.5, and we'd have 0.5 squared plus 1 squared plus 1.5 squared. Alright, boring, right guys? Yep, you got it. But we're just adding up from 1 to 8, 0.5 times, in this case it's just going to be I squared, or it's going to be f of x. So in this case here, the f of xi is just squaring the value. Okay, so you can see the working on the next page here, adding all those 8 up, and we get 25.5 for the approximate result. So let's say we use 16 rectangles, 20 rectangles, you can see we'd get a much better approximation. And in fact, what they did early on is that they looked at, okay, let's use 8 rectangles, let's use 20, let's use 30. What value are we tending towards? What's that value heading towards? The right rectangles and the left rectangles, the more you use, it's heading towards a particular value. That value is the area underneath the curve, the exact area under the curve. Okay? So we can do this on our CAS calculators as well. If we want to do 100 rectangles, we could get our calculators to do the work. All right? And so this little example shows how on a CAS you could work out the area underneath the curve, in this case from 3 to 1 of 5x cubed, just by using the sum formulas and adding up all the areas of those rectangles. So here's the grand connection here. Let's go back to that original graph where we have the velocity is the velocity time graph, and here we've got a specific example where the velocity is 2 times the time. Okay, so every, let's say we're doing time in hours, so after 1 hour, or let's say we're doing it in times in minutes. So after 30 minutes, we're going to be doing 60 kilometers a minute, or whatever it is. When t is equal to 60 minutes, we're going to be doing 120 kilometers per minute. So we use kilometres per minute here to make it easier. Okay, so if that's the velocity time thing that we're always going to be doing, the question is, how far have we travelled after t minutes? So again, I could work out the area under the curve to work that out. And it turns out that if you work that out at 30 minutes, you'll get 900 kilometres. If you work that out at 40 minutes, you get 1600 kilometres. Work that out after 2 minutes, you would have gone 4 kilometres if you keep that profile. In other words, if your speed is always 2 times the time. And pretty soon, you can start to see a pattern forming in these things. Okay, so this is time and this is the distance travelled. You could see that the distance travelled is always the time squared, right? And that is the case. If your velocity is always 2t, then the distance you've travelled is t squared. Now that was a really big breakthrough. In fact, what they've discovered, and you might see the connection between those two, we know that when we differentiate t squared, we get 2t. So this thing here is an antiderivative of t squared. And so it happens that if you have the velocity as t squared, then the distance travelled is always t cubed over 3. Brilliant. Makes life a lot easier. Hence this formula here. If we want to work out the, and this is called a definite integral now, where we've got numbers here, b and a, so we're talking about the area underneath the curve. What we do is we find an antiderivative of this function f of x, like I've just shown you. We substitute in b, so it's like asking the question, this one above, how far have we travelled between 60 minutes and 30 minutes? Well, we work out where we are, or let's say 40 minutes and 30 minutes. We work out where we were at the 40-minute mark, we work out where we were at the 30-minute mark, and we subtract. That'll tell us that we travelled 700 kilometres in that time. Similarly, for this formula here, we do the same thing. We find out where we are at the top and subtract off where we were at the bottom. And that gives us the definite integral, or the area underneath the curve. So in this first example here, the integral from 5 to 0 of x squared, this is the way you need to write it. First of all, we want to find the antiderivative of x squared, which is x cubed over 3. Alright, the square brackets, and then 5 and 0. That means we've done the integral, and now we substitute in 5, minus, we substitute in 0. So we get 125 over 3. And that's our final answer. That gives me the exact area underneath the curve y equals x squared between 5 and 0.